Hi, I am Dr. Abhishek Joshi, and in this video lecture we are going to discuss about the concept of matched filter. So, we have to start with the optimum linear detector for binary polar signaling. So, for binary polar signaling we know that we are using plus V and minus V for representing the 1 and 0. So, the probability of error, also known as a bit error rate, is a directly quality measure of the communication system. So, at the receiver side we know that we are receiving the pulses, that is plus minus Pt plus Nt. When we are passing through the filter, that is having the function, that is h of f represented by St, is given by plus minus the output of the filter is given by P naught t plus N naught t, where N naught t is a noise and here Nt is a noise which is added due to the channel, and we are sampling at the time instant, that is t is equals to Tm, and the threshold device we are using to check whether the value is greater than 0 or less than 0. If the value is greater than 0, then we will say it is 1. When the value is less than 0, we will say it is 0. So, this we are using to take the decision whether the bit is 1 or 0. So, here we have the pulse at the receiver side represented by Pt plus Nt, and this dashed line pulse is showing the actual pulse. After the addition of the noise, the pulse distortion can be seen. Here we have the dip, and the duration of the pulse is from 0 to t naught, that is to t. When we are passing through the filter, what is happening is at the sampling instant we have increased the power, or it is after the filtration we are having the maximum power at the sampling instant, that is t is equals to Tm. So, this is the output of the filter given by P naught plus N naught t. So, in binary communication system, the information is transmitted as 0 and 1 in each time interval, that is t naught. To begin, we consider the binary polar signaling as shown in the figure, which is we have seen, in which the source signal, the bit 1 and 0 are represented by the plus minus Pt respectively. Having passed a distortion less but a noisy channel, the received signal waveform is given by. So, at the receiver side we have the expression given by the output, that is Yt plus minus, that is equals to plus minus Pt, that is having the pulse, and Nt is the noise due to the channel. For the bit duration, that is from 0 to t naught. So, where Nt is a Gaussian noise channel. Okay. So, when we are passing this pulse Yt through the filter, that is filter response given by St, we are getting Yt as, that is plus minus Pt, that is a pulse due to the polar signaling. For polar we are representing plus minus voltage. Okay. So, we are representing it by plus minus Pt into the filter response, that is St, and the output is given by P naught t plus Nt, the noise, multiplied by the filter response, and the output of the noise is N naught t. So, we are representing the pulse with the noise with the filter response, that is plus minus P naught t, and the noise after the filter is given by N naught t. So, the output noise and the pulse is given by P naught t and N naught t. The decision variable of this linear binary receiver is the sample of the received filter output, that is at the sampling instant t is equals to Tm. So, the received pulses at the sampling instant, because here we can see we are sampling it at a regular time interval, that is t is equals to Tm. So, here we have the received pulse, that is given by, or you can say before the after the sampling we are having the received pulse given by Rtm, that is equals to plus minus P naught Tm plus N naught Tm. So, based on the properties of the Gaussian variables, that is N naught T, that is equals to, so we can represent our noise in terms of when we are passing through the filter, it can be written as from 0 to t n tau h t minus tau d tau. So, it's a Gaussian with a 0 mean as long as n-t, where n-t is the noise, which is a Gaussian noise. So, it is having the 0 mean. Okay. So, if you define, so we are defining the pulse by AP, that is equals to P naught Tm, and the variance is given by sigma n square, that is the expectation of n naught Tm whole square. So, which is to be 0 or 1, then the optimum threshold detection, that is given by the RTM, that is a pulse. So, we have to take the detection. So, we are representing by DEC for detection. So, we are having 1 if the received pulse at the sampling instant is greater than equals to 0, then we will say it is 1. If it is less than 0, then we will say it is 0. So, this decision we have to take at the sampling instant, that is t is equals to Tm. Whereas, the probability of bit error is given by Pe, that is equals to the Q function of rho, where we know that this rho is nothing but the ratio of the pulse amplitude or signal strength divided by the variance of the noise. Okay. So, this is the signal strength or pulse strength, we can say, and sigma n is the variance of the noise. Okay. To minimize Pe, we need to maximize, that is rho, because the Q function of rho decreases monotonically with rho. So, let the received pulses, that is Pt, be a time limited. So, we are considering the time limited pulses to T naught to minimize the BER, that is a bit error rate or the probability of error. We should determine the best receiver filter, that is h of f, and the corresponding sampling instant, that is Tm, such that QP is minimized. So, in other words, we seek the filter with the transfer function that maximizes, that is rho square, where rho square is the ratio of the signal to the noise variance. So, it is given by, that is P naught Tm, or you can say the whole square of the term, divided by the sigma n square. So, which is coincidentally also known as the signal to noise ratio, because actually we are taking the ratio of the signal, or you can say the pulse divided by the noise at the time instant, that is t is equals to Tm. So, first denote that Fourier transform of Pt as P of f, the PSD of the channel noise and T as SNF will determine the optimum receiver filter in the frequency domain, starting with, so we are starting with, that is the output pulse is given by the inverse Fourier transform of the pulse in the Fourier domain, or you can say the frequency domain, that is P of f, and h of f is the transfer function in the frequency domain, and that is h of f. So, we can expand using the Fourier transform, inverse Fourier transform formula. It is given by integration from minus infinite to plus infinite P of f, h of f, e raised to power j 2 pi f t d of f. So, we have the sample value at the sampling instant given by t is equals to Tm, P naught Tm equals to integration from minus infinite to infinite h of f, P of f, e raised to power minus j 2 pi f Tm and d of f. On the other hand, the filtered noise has the 0 mean, which is given by n naught t bar. So, this bar can be written as the expectation of n naught t. So, expectation is same as the mean. So, which is equals to the whole expectation or the whole bar. Then expectation, we know that formula, that is expectation of x is nothing but, it is given by integration from minus infinite to infinite x f of x dx. So, same thing we are using here, we are using the same. So, n naught we have. So, integration from the sampling time period, that is from 0 to t, n tau h t minus tau d tau. This is the time interval. So, we are taking the integration. So, this whole bar we can take inside the integration. So, when we are taking the mean of the filter, it will be the mean exactly the same, nothing will be changed, but Here the random variable is the noise. So noise is actually a random process, that is a Gaussian random process, as we know. This is not a random, this is a definite, so the average will be the same thing, but here this is the random process, so we have to take the mean. So this mean, that is noise whole bar, that is equals to 0, because we know that the mean of the noise, that it is a Gaussian random noise, is equals to 0, while its variance is given by, that is sigma n square, that is equals to n naught square t whole bar, that is equals to integration from minus infinite to infinite s n f h f whole square df. So the signal to noise ratio is given in the frequency domain, which can be represented as, that is rho square is equals to, that is integration, that is a signal, this is the expression for the signal which we have got here. So here we can see the expression of the signal, that is integration from minus infinite to infinite p of f h of f e raised to power minus j 2 pi f t m d of f. So same thing we have written here. So here we have integration from minus infinite to infinite h of f p of f e raised to power minus j 2 pi f t m d of f whole square divided by the noise variance, which is given by integration from minus infinite to infinite s n f h of f whole square df. Okay. So the Cauchy-Schwarz inequality is very powerful tool to find the optimum filter h of f. So we can simply identify, that is x f is given by, that is h of f and under root s n f. So we are considering, we are actually using or resubstituting the in terms of x and y. So and yf is given by p of f e raised to power j 2 pi f t m and by under root s n f. Then by applying the Cauchy-Schwarz inequality to the numerator, the rho square can be written as, so rho square is equals to, in terms of x and y we are representing it. So we have integration from minus infinite to infinite x y h y of f d of f whole square divided by integration from minus infinite to infinite x f whole square d of f. So this should be less than, so signal to noise ratio should be less than. So we are writing in terms of, so we can write that the power of x and y whole square is less than equals to the x into y. So this is the Cauchy-Schwarz equality. So this property we are using directly here in this. So what we have, so we have written the same thing, but here we have integration. So integration from minus infinite to infinite and x f whole square df, that is the energy, and integration from minus to infinite to infinite y of f whole square df divided by integration from minus infinite to infinite x f whole square df, and we have the integration from minus infinite to infinite y of f whole square df. So the y of f we know that, so directly we can substitute the value of y of f here, that is given by integration from minus infinite to infinite p f whole square divided by s n f, that is the power spectral density of noise. Here we have then pulse in Fourier domain. Okay. So with an equality, or with the equality that if and only if when x f is equals to k times of y f. So we can write h of f, that is substituting x f, that is equals to k times of y f, substituting this thing. So we have k times of y f given by p of f e raised to power minus j 2 pi f t m divided by under root of s n f, that is equals to k times p of minus f e raised to power minus j 2 pi f t m divided by under root of s n f. So hence the SNR, the signal to noise ratio, is maximized if and only if, that is HF is equals to k times of p of minus f e raised to power minus j 2 pi f t m, where k is an arbitrary constant. So this optimum receiver filter is known as the matched filter. So the optimum result states that the best filter at the binary linear receiver depends on the several important factors, that is the noise, power spectral density SNF, the sampling instant Tm, the pulse shape P of f. So these are the three important things which we have to keep in mind while designing a matched filter. So first thing is the noise power spectral density, that is SNF, the sampling instant Tm, the pulse shape P of f. So it is independent of the gain of the receiver, that is k. So gain of the receiver we have considered, that is k, since the same gain would apply to both of the signal and the noise without affecting the signal to noise ratio, that is SNR. So for the white channel noise, SNF is given by, that is SNF is equals to the noise power divided by 2, which becomes, that is rho square. Rho square is nothing but the signal to noise ratio, that is less than equals to rho square maximum, and here we have substituted the value of SNF, that is n by 2, integration from minus infinite to infinite P of f and df e raised to power, that is 2 times the energy, because we know that P of f whole square is nothing but the pulse energy divided by the noise power. So where we have this EP as the energy of PT, and the matched filter is simply given by h of f is equals to k prime P of minus f e raised to power minus j 2 pi f Tm, where k prime is equals to twice of k by n, which is an arbitrary constant. So here we have the optimum choice for the sampling instant, that is given by P of t, which is having the pulse from 0 to t naught. Here we have the pulse. When we are representing for the negative period, it is given by P of minus t, and for the sampling instant, so it is shifted to the sampling instant, that is Tm, so Pt m minus t, and this Tm minus t can be further expanded as at the sampling instant, that is Tm equals to T naught. This is Tm is less than T naught, and here there Tm is greater than T naught. So here more shifting we can see here. So the unit impulse response h of t of the optimum filter is obtained by the inverse Fourier transform. So inverse Fourier transform is given by h of t, that is inverse Fourier transform of k prime P of f e raised to power minus j 2 pi f Tm. Note that P of minus t and the Fourier transform is given by P of minus f, and where e raised to power minus j 2 pi f Tm represent the time delay of Tm seconds. Hence we can write that is ht is equals to the k prime P of Tm minus t, and the response P Tm minus t is the signal pulse, that is Pt delayed by Tm. So we have three cases as we have seen in the figure, that is the sampling instant Tm is less than T naught, the sampling instant Tm is equals to T naught, and Tm is greater than T naught as shown in the figure. So this is the last case where we have Tm is less than T naught yields a non-causal impulses response which is unrealizable. So although the other two cases yields the physically realizable filters, the case is Tm is greater than T naught delays the decision making instant, that is Tm unnecessarily. So Tm equals to T gives a minimum delay for decision making using a realizable filter. So in our future discussion we will be seeing. Observe the pulse, that is Pt and Ht. We have the width, that is T naught seconds. So hence P naught, which is a convolution of Pt and Ht, has a width that is twice of T naught seconds, with a peak occurring at t is equals to T naught, where the decision sample is taking also that the pulse, that is P naught f, that is equals to Pf into Hf, which is given by k prime of Pf whole square e raised to power minus j 2 pi f T naught, and P naught t is symmetrical about t is equals to T naught. So hence we have the signal to noise ratio with a gain, that is k prime equals to 1, we are getting Ht as P of T naught minus t, or equivalently we can write the filter, that is a matched filter having the response given by P of minus f e raised to power minus j 2 pi f T naught. So for which the signal to noise ratio is maximum at the decision making instant, that is C equals to T naught. The matched filter is optimum in the sense that it maximizes the signal to noise ratio at the decision making instant. Although it is realizable to assume that the maximization of this particular signal to noise ratio will minimize the detection of error probability. So it is have not proven that the original structure of the linear receiver will be the threshold detection in the optimum structure. So, given the match filter under the white Gaussian noise, the filter, that is a match filter receiver, leads to the maximum, that is a power maximum, as well as the minimum BER of given by the probability of error, that is having the Q function, that is P of maximum, that is rho maximum, and Q, that is under root of 2 E by N. So, this is quite remarkable. It shows that for the system performance is considered, the matched filter receiver is given by the expression, that is a energy of the pulse, that is integration from minus infinite to infinite P of f whole square d of f, that is equals to integration from 0 to t naught P of t whole square dt. So, the matched filter may be implemented with the alternative arrangement as shown in the input of the matched filter. The output RT is given by, that is integration from minus infinite to infinite y of x h of t minus x dx. So, where ht is given by the p of t naught minus t, and ht is can be written as, that is p of t naught minus tx, that is equals to the delay of the pulses, that is p of x t naught minus t. So, finally, we can write the correlation detection, that is equals to y of t at the receiver side, that is plus minus represented as plus minus pt plus nt, that is noise, and when again we are multiplying with the pulse, what we are getting? We are getting the square of the pulses, and here we are passing through the low pass filter, and then we are getting this RF, or we can say this is nothing but a matched filter sampling at the instant, that is t is equals to t naught, and what we are getting, that is received pulse, that is at RT naught, and the threshold device, and after the threshold device we have to take the decision. So, this is the best example of the matched filter, that is a correlation detection. So, we can write for the correlation detection RT, that is integration from minus infinite to infinite pi of x and p of x t naught minus t, and RT at the sampling instant, that is y of x p of x dx whole integration from minus infinite to infinite, and Rx t naught for integration from minus t naught 0 to t naught y of x p of x dx. So, in this lecture we have discussed about the matched filter, the correlation receiver. So, here we are going to stop this lecture. Thank you.